Hello, Rancho Verde. It's Mr. Langston again, coming at you to teach the calculus class. We are now doing section 2.2 of the textbook, and the first thing we've got is a warm-up. So you need to sketch the graph of f of x is equal to x squared plus 4x plus 4. So we're going to do exactly what we did last time in section 2.1, which is complete the square. So to complete the square, first thing we're going to do is we have f of x is equal to, by the way, when I said sketch the graph, did I even include anything in terms of graphing? Nope, I did not. Okay, so I didn't include a coordinate plane. Oops, we're just going to roll without that. So first thing we're going to do on this one is we're going to take the first two terms and we're going to put them in a parenthesis. So we're going to separate them out. So we got x squared plus 4x, and we're now going to take the last term and put it outside here. So m parentheses plus 4. And now we're going to write it as f of x is equal to, in this case, x squared plus 4x plus blank minus blank, and now plus 4. So we're going to take the middle term, and the middle term is 4, and we will now divide it by 2 and then square it. And that is what goes in here. So 4 divided by 2 is 2. Quantity squared is 4. So it's plus 4 minus 4. Now there's nothing in front of this parenthesis, so that's great because now we can just take the last term and we can move it out of the parentheses. So we have f of x is equal to x squared plus 4x plus 4. And now we've got outside plus 4, and we have the one that we moved, which is minus 4. Now, we're going to rewrite this as a square, and to do that, we're going to square root the last term, and we're going to take the sign of the middle term. So we have x plus square root of 4 is 2, quantity squared. And in this case, plus 0. So we have our vertex, which is, in this case, negative 2, 0. So if I wrote this on a coordinate plane, and I'm going to write my coordinate plane, I'm at negative 2, 0. So negative 2, 1, 2, right there. And now, the rest of the graph, it opens, in this case, upwards. So we're going to go out 1, up 1, out 1, up 1, out 2, up 4, out 2, up 4, and our graph will look something like that. There you go. So, on section 2-2, we're doing polynomial functions of higher degree, and our focus standard is still chapter 2, polynomial and rational functions, and we're going to model with mathematics, and you're going to be able to describe the graphs of polynomial functions with degrees of 3 or higher. So there's a lot of content that I have on here that's not part of your notes, because honestly, your notes are kind of lacking on this section. So you need to find the real zeros of polynomial functions. So for a polynomial function f of degree n, the function has at most n real zeros, and the graph of f has at most n minus 1 turning points. Now, when I say a turning point, I mean a local maximum or a local minimum. And what I mean by local is, I mean it's not an absolute maximum or minimum. It's not like the highest max of the graph or the lowest minimum of the graph. The graph might have it, might not have it. But if I just look at a small point, so for instance, here's my coordinate, and if I have this and this and this and this and this, each one of these are turning points, because there's going to be a maximum value or a minimum value. And it's a turning point because it's where it goes up and then it goes down and up and down and up. So it starts changing direction. So in this section, we're going to study basic features of the graphs. First thing to know is continuous, which means basically there's no breaks. So I have every polynomial function. Well, in this case, the polynomial functions, it won't have any breaks, holes, or gaps. It's going to be continuous. It's going to flow nicely. Another thing you need to know is that all the terms are rounded. Polynomial functions are like roller coasters. You're not going to get like that. It's not going to do that. It's a roller coaster. They're going to be smooth. So it's going to go up, and it can be really steep. And then it's going to drop down, up, down, up. So it doesn't matter if it's steep, but it needs to be smooth. So an even function. First off, what you need to understand is for these functions, if I have y equals x squared, that's going to give me a parabola. Y equals x to the fourth is going to give me, well, it's going to give me a parabola too. Y equals x to the sixth is going to give me a parabola. The higher I go up with the even exponents, the steeper it's going to be when you get out to the right, but also the flatter it's going to be when you get closer to the vertex. So notice I have this one here. It's not as steep as y equals x to the fourth, and it's also not as flat when I get closer to the vertex. So steeper out farther and flatter when I get closer to the vertex. And it's actually the same here with an x cube, even though it doesn't necessarily have a vertex. I mean, it kind of has a middle point, shall I say. So it's going to be steeper as I'm out to the right. For instance, y equals x cubed, here's that, and I have y equals x to the fifth right here. So it'll be steeper, and then when it gets to the, quote, middle, it will be flatter. And then it'll go steep again. Okay, so that's something you should know about higher degree polynomials. Also, what you also need to understand is this part here. First off, the leading coefficient determines the basic shape. And when I say the basic shape, I mean it determines if it's going to look like that or if it's going to look like that. The leading term tells you. Everything else here, it adds wonkiness, or maybe it's K-E-Y-N-E-S-S, whatever. It's wonkiness. And what I mean is when I say it adds wonkiness is it adds to the middle the wobbles, the maximums, the minimums. It adds the weird stuff that goes on all throughout here. Okay, so those terms add our wonkiness, but the shape is determined by the first term, the leading term. If the leading term is odd, when I go far to the right, it's going to go up. When I go far to the left, it's going to go down. Now, that is if A sub n, is positive. Now, if A sub n is negative, it's going to climb on the left, and it's going to dip on the right. And all the wonkiness is added by everything else right here. Now, if the leading term is even, okay, assuming the leading term is even, so this term right here, if it's even, and when I say even, I mean the power is even, then it's going to, if A is positive, it's going to climb on the left and it's going to climb on the right. And that's if A is positive. Now, if A is negative, it's going to drop on the left and it's going to drop on the right. And again, all this wonkiness is added by the other stuff right here. This adds wonkiness. So what we're going to do is right here, we're going to describe what happens on the right-hand side and on the left-hand side for the graph. And so when we do that, we look at the leading term. Now, the power is odd. So I know if the power is odd, it's going to look like one of these two. And A is negative, or A sub n is negative. So I now know it's negative, so it looks like this one here. So on the left, it's going to go up, and on the right, it's going to go down. Let's look at this one, x to the fourth. So A is positive, and the power is 4, so it's even. So it's going to, on the left, it's going to climb up, and on the right, it's going to climb up. For this one, I have x to the fifth, so A is positive, the power is 5. So I know that on the left, it's going to go down, and on the right, it's going to go up. It's going to look something like that. So now, like we said previously, the function is a polynomial function, so it has at most n real zeros. And when I say zeros, I mean roots or x-intercepts. They're all zeros. And I have at most, and understand, at most, n minus 1 turning points. And when I say turning points, I mean local max or minimum. So I have the question here. It says find the real zeros of the function. All right. So all we do is we take and set it equal to 0 and solve for x by using the F word in math, which is factoring. So I'm going to pull out a 2x squared from this entire equation. So I have 2x squared. And you know what? I'm just going to pull out a negative 2x squared to make things better. So when I pull out the negative 2x squared, well, I ask myself, negative 2x squared times what gives me negative 2x to the fourth? So that's going to give me x squared. And then I say negative 2x squared times what is going to give me positive 2x squared? So that's minus 1. And now I have x squared minus 1. So that factors out into, and I'm going to change it to a darker color, negative 2x squared, x minus 1, x plus 1. And now I set each of these equal to 0. So negative 2x squared equals 0, x minus 1 equals 0, x plus 1 equals 0. So x equals negative 1, x equals 1, and x equals 0. So these are my roots. I've got 3 roots. Notice my power is 4, but I can have at most 4 roots. This, because it has a power of 2 right here, this is a multiplicity. A multiplicity. Okay? This one has a power of 1. This is just a normal root. Normal root. This one's a multiplicity because I got a power of 2 when I factored it out. So, these are my roots. I have 3 roots. It's okay because I can have at most 4 roots. So, oh, here's the solution. I forgot I had that in there. So I've got my roots. Let me actually make this just a bit smaller so you can read it. And that's not working out. So let's actually push it there. So I've got my roots right here. Okay. Notice I have my 0, I have -1, and I have 1. Now, this 0 I want to talk about. So, the repeated 0. Basically, when I'm talking about repeated zeros, I mean my multiplicities. I call them multiplicities. They call them repeated zeros. Just know both. So, when my repetition of my power is odd, the graph is going to cross it. When my repetition of my power is even, my graph touches, or I call it, bounces off the x-axis. Now, what I'm talking about is here. Look right here. So I had -2x squared, x minus 1, x plus 1 when I factored. Notice, I have my multiplicity here. Its power is 2. It's even. So it's going to bounce off the x-axis. For this one, my power is 1. Same thing here, my power is 1. It's odd, so it's going to cut my x-axis. So that's what I mean when I say this. So which equation in this one, which equation matches the graph? Well, it climbs on the right, it descends on the left, so its leading term is odd. So that gets rid of this because it's a square, and that's even. Nope, it's got to be one of these. Now, how many turns does it have? It has 1, 2, 3, 4. And remember, n minus 1 turns. So that means n minus 1 is equal to, in this case, let's say 4. So n has to be 5 in this case, or higher. And the reason it's or higher is because it has at most n minus 1 turns. Okay? So it can be greater than or equal to 5. Well, that means the leading term here is 3, so that's out. So my answer has to be B. And that's all the notes I have for you, Rancho. So I appreciate your time. Thank you very much. I hope you like this, and I hope it was informative. So if you have any questions, you can send me an email or talk to me after class. And that's about it. Have a great weekend. Peace.